If everything in the universe had gone according to physics script, you wouldn't be here. Neither would I. Neither would this video. The air you breathe, the stars in the sky, every molecule in your body. None of it should exist. At least, not alone. Imagine for a moment that the universe was like a perfectly balanced deck of cards. For every particle of matter created at the beginning of everything, there should have been one of antimatter. As if every red card came paired with a black one. A kind of cosmic mirror, with opposite charges, but the same properties. Except, for some reason, the universe chose a side, and antimatter simply disappeared. But did it really vanish? Or are we just looking at it the wrong way? In recent years, experiments conducted at CERN, the world's largest particle physics laboratory, have been diving deep into this mystery. What's being discovered is fascinating and at the same time, frustrating. Antimatter exists, it can be created, it can be studied, but it still refuses to tell us why it lost this cosmic battle. Today, we're going to dive into this story. From Dirac's mathematical prediction to the behavior of antihydrogen in gravity, going through fundamental forces, quarks and positrons, particle detectors and theories that border on science fiction. We're going to discover what's really happening with antimatter at CERN, and why this could change everything we thought we knew about the universe. Everything you see, from your phone screen to the most distant galaxies, is made of particles like protons, neutrons, and electrons. It's as if you were seeing only half of a photograph, and, according to the laws of physics, this should be only half the story. The other half would be composed of antimatter. A mirrored universe, with the same particles, but with opposite charges. Think of it as if every person in the world had an identical twin, but with a completely opposite personality. Still, when we look around, we don't find this B-side of reality. Antimatter seems to have disappeared right after the Big Bang. This enigma is known as baryon asymmetry, one of the main questions in modern cosmology. To understand better, baryons are the heavy particles like protons and neutrons that form ordinary matter. The asymmetry means there's much more matter than antimatter in the observable universe. It's as if half the guests at a giant party had simply evaporated, leaving only one side of the table occupied. If matter and antimatter emerged in equal quantities, where did all the antiprotons, anti-electrons, and anti-neutrons that should be here go? Would they have annihilated with their normal versions? In that case, why did anything survive? Why isn't the universe just a sea of empty photons, the result of billions of annihilations between particles and antiparticles? What we know is that something at some point broke the symmetry. And this break wasn't small. It was enough to allow the formation of all the matter we know. It's as if the universe were a pair of perfectly balanced scales, and someone placed an extra grain of sand on one of the sides. This cosmic grain of sand allowed you to be here, reading this right now. The current challenge is to understand what caused this imbalance. Could it be some flaw in CP symmetry during the first moments of the universe? Some undiscovered particle that interfered with fundamental interactions? A hidden force? Whatever the answer, it's still hidden, perhaps right there, between the frozen walls of a particle accelerator at CERN. The idea that there could exist an inverted version of matter didn't emerge in a laboratory, but in equations. It's as if mathematics had whispered a secret about the universe before we could even hear it. In 1928, Paul Dirac, trying to reconcile quantum mechanics with relativity, came to a strange conclusion. His calculations predicted particles with negative energy. Imagine trying to solve an equation and discovering that the answer includes negative numbers where there should only be positive ones. For a long time, this was seen as a mathematical anomaly, an error in the calculations, until 4 years later, the unexpected happened. Carl Anderson, analyzing traces left by cosmic rays in a cloud chamber, found something that looked like an electron, but with positive charge. The cloud chamber works like a kind of footprints that particles leave when passing through, allowing scientists to see the invisible path of subatomic particles. It was like finding a person who walks backwards, but in everything else is just like you. It was the positron, the first experimental glimpse of an antiparticle. This moment changed everything. If the electron had a charge-inverted twin, what prevented protons and neutrons from also having their equivalents? And more. Could they combine in the same way, forming antimatter atoms? The answer came gradually, like pieces of a cosmic puzzle fitting together. With the advancement of particle physics, we discovered something fascinating. Every fundamental particle has an antimatter counterpart. From the quarks that make up protons, imagine them as microscopic bricks that combine to form larger particles, to the almost undetectable neutrinos. These neutrinos are like ghosts that pass through your body at this exact moment, coming from the sun and other stars. Thus were born the concepts of antiprotons, antineutrons, and even antihydrogen. With this, particle physics took a leap. The universe stopped being just a field of forces and masses, and became also a game of symmetries. The discovery of the positron wasn't just a technical achievement, but a confirmation that Dirac's equations pointed to something real, something that was out there, waiting to be found. And now, almost a century later, this search has become a true technological race. Particle accelerators and ultrasensitive detectors hunt antiparticles in the most unlikely places. What they're discovering will surprise you. Despite its intimidating name, antimatter is not a chaotic or unpredictable entity. In fact, it follows the same rules as ordinary matter, just in reverse. It's like having a car that works exactly like yours, but with reverse gear in place of first. An antiproton has the same mass as a proton, but negative charge. A positron behaves like an electron, but with positive charge. In the laboratory, when we managed to produce and maintain antiparticles for long enough, they proved to be as stable as their normal sisters, until the moment they meet, of course. Then comes the famous annihilation, and everything turns into pure energy, following Einstein's most famous equation, E equals mc squared. It's like two magnets of opposite polarities that, when they touch, simply cancel each other out in an explosion of light. This obedience to rules becomes even more fascinating when we take into account the extreme environment where these particles are produced. In particle accelerators, like the LHC at CERN, collisions at extremely high speeds generate moments that resemble the primordial chaos of the Big Bang. Imagine two bullet trains colliding head-on, but instead of wreckage, completely new particles emerge from the pure energy of the collision. It's in this scenario that antiparticles emerge for thousandths of a second that soon collide and disappear. But with current technologies, we manage to capture some of them. It's like trying to catch raindrops with a fishing net. We can even form entire atoms, like antihydrogen, combining an antiproton with a positron. What's leaving scientists perplexed is that these experiments have shown that antimatter responds to electromagnetism, the strong force, and even the equivalence principle of general relativity, just like ordinary matter. This, by itself, is already a surprise. Many expected to find more glaring differences. But no, antimatter is well behaved, almost too polite. And precisely because of this, it intrigues so many physicists. If it's so similar, why was it discarded by the universe? This question leads us to something deeper, the fundamental forces and how they treat these particles. This is where the story gets really interesting. On the grand stage of physics, four fundamental forces conduct the cosmic spectacle. Think of them as the four elements that govern everything in the universe: gravity, electromagnetism, strong force, and weak force. It's as if there were four different conductors, each conducting their own orchestra of particles and interactions. In general, these forces make no distinction between matter and antimatter. The strong force, for example, the one that keeps atomic nuclei stuck together despite the electrical repulsion between protons, holds quarks and antiquarks in nuclei the same way. It's like a universal glue that doesn't care if you're gluing regular paper or mirror paper. As for electromagnetism, responsible for everything involving charges, from the magnet on your refrigerator to the lightning that cuts through the sky, it attracts the positron to the antiproton the same way it attracts an electron to a proton. Here, matter and antimatter dance exactly the same step, like two couples doing the same choreography on opposite sides of the ballroom. But when we get to the weak force, the scenario changes completely. This force, which governs processes like radioactive decay when unstable nuclei crumble, releasing energy, introduces a fascinating peculiarity: chirality. Imagine particles that spin like screws, some threading to the right, others to the left. It's as if it had a preference for righties or lefties in the world of particles. It prefers particles with a certain type of spin, or rather, handedness. Physicists say, almost poetically, that the weak force only interacts with left-handed particles and right-handed antiparticles. It's like it were a very specific doorman who only lets in people who wave with their left or right hand, depending on whether they're from group A or B. This breaks an important symmetry, called CP symmetry, a fundamental rule that says the universe should treat particles and antiparticles equally if we invert their charges and look at them in the mirror. And since 1963, we know this imbalance is real. It appears in experiments with mesons, short-lived particles that exist for fractions of a second, and is one of the few clues that the universe does indeed have a certain preferred side. This symmetry breaking is subtle, but powerful. After all, if there exists a force that treats particles and antiparticles differently, maybe there lies a clue to this baryon asymmetry. Maybe the weak force, even being the most delicate of the four, had a weighty role in the first milliseconds of the universe. Still, current models show that this difference isn't sufficient to explain the total absence of antimatter. It's like having a scale with a slight imbalance, but not enough to knock all the weights off one side. This leads us to think, what if there's another hidden force, or if gravity also holds a surprise? That's exactly what scientists decided to test in the most direct way possible. Among all fundamental forces, gravity is the most mysterious, and perhaps the most poorly understood. It dominates the cosmos on a large scale, curving space-time and keeping planets in orbit, but it's incredibly weak when compared to other forces. It's as if it were a whisper amid screams. To get an idea, the electrical force between two protons is 10 to the 36th power times stronger than the gravitational one between them. It's the difference between a hurricane and an almost imperceptible breeze. For this reason, for decades, measuring its effects on antimatter was almost an impossible mission. Still, a question persisted among physicists and cosmologists. Does antimatter fall upward? In other words, is it repelled by ordinary matter instead of attracted? Imagine if antimatter were like a helium balloon in the world of gravity, always trying to float away from normal matter. The hypothesis was bold, but intriguing enough to motivate high-level experiments. That's how the Alpha experiment at CERN was born. The objective was simple in theory, but incredibly complex in practice. Directly measure the effect of gravity on antihydrogen, a neutral atom formed by an antiproton and a positron. Being electrically neutral, antihydrogen avoids electromagnetic interference. It's like isolating a single voice in a packed stadium. This is crucial, since any push outside of gravity could compromise the results. The challenge was to keep these atoms floating in an ultra-controlled environment, practically without external influence. It's like trying to balance soap bubbles in a room where even the slightest breath of air could ruin everything. And then, at the crucial moment, release them to see, do they fall down or up? The result came with unprecedented precision. In 2023, researchers announced that about 75% of antihydrogen atoms fell downward, with an acceleration of approximately 0.75 g, still within the margin of error for normal gravity. It's as if you dropped an apple, and it fell almost at the expected speed, but not perfectly. This suggests that antimatter is pulled toward the ground, just like matter. No negative gravity or mysterious cosmic pushes. It was a relief for those who defend the equivalence principle of general relativity, but also a small disappointment for those who were rooting for a revolution in physics. If not even gravity makes a difference, the mystery continues. But this leads us to an even more intriguing conclusion. After so much effort, dozens of experiments and decades of theories, we've reached a provisional but powerful conclusion. Antimatter is surprisingly similar to matter. It's like discovering that your reflection in the mirror not only looks like you, but acts exactly like you in almost all situations. The four fundamental interactions, notably electromagnetism, the strong force, and now even gravity, treat antimatter the same way they treat matter. The only exception continues to be the weak force, with its strange preference for left-handed particles and right-handed antiparticles. But even so, this observed difference is too small to explain the asymmetry of the universe. Think about this for a moment. This means that, in a parallel universe made entirely of antimatter, stars would shine, planets would orbit, and even antimatter beings could exist, following the same physical laws that govern our reality. It's as if there were two identical movies being shown simultaneously, but we can only watch one of them. With this, more radical theories are being discarded one by one. The hypothesis that antimatter could have negative gravity, for example, lost strength with data from the alpha experiment. We're also increasingly confident that CPT symmetry continues to hold. That is, the fundamental laws of physics remain symmetric if we invert charge, parity, and time simultaneously. But here's the paradox that's keeping cosmologists awake at night. If everything is so symmetric, why is the universe so asymmetric? Where are the antiprotons and antiquarks that should have survived the Big Bang along with their matter pairs? It's as if half the actors in a theatrical play had simply disappeared from the stage, leaving only one side of the story being told. What remains, then, is the relentless search. Science doesn't close a question just because it hasn't found the answer. Quite the contrary. It continues digging, excavating, investigating every clue. It's like a detective who, even without finding the culprit, continues analyzing every piece of evidence, whether through increasingly sensitive particle detectors, capable of capturing the universe's faintest whispers, computer simulations that recreate the first moments after the Big Bang, or new versions of the Standard Model. Physicists continue trying to understand why we exist. Maybe the key lies in still unknown forces, hidden in dimensions we can't perceive. Maybe in particles so exotic that we'll only see them when we update our way of observing the universe. Or maybe the answer lies in something so simple and fundamental that we're passing by it without noticing. What we know is that each experiment at CERN, each particle collision, each anti-hydrogen atom created and studied, brings us a little closer to the truth. It's as if we were assembling a cosmic puzzle, piece by piece, even without knowing exactly what the final image will be. Antimatter forces us to face a profound truth. No matter how much we advance, no matter how much we unravel the secrets of the cosmos, the universe still holds mysteries that could completely change our understanding of reality, and many of them remain well beyond our reach. But it's precisely this search, this discomfort with what we still don't know, that moves science. Each experiment at CERN, each particle collision, is an attempt to understand why we're here and why we're made of something and not nothing. Think about this. Your existence may be the result of an asymmetry so subtle, so specific, that we're still trying to understand it. You are, literally, the product of a cosmic imbalance that allowed matter to survive the primordial chaos of the universe. The question persists: why did the universe choose matter? Maybe the answer is still waiting for us, hidden in a quiet corner of the observable or invisible universe. And until it comes, all we can do is continue exploring, questioning, learning, and marveling at what has already been discovered. After all, knowing that antimatter behaves like matter may seem like little for those seeking definitive answers. But for those who understand that each discovery is a step toward the unknown, this brings us closer to something much greater. Understanding why we exist in a universe that, according to the laws of physics, should be empty. And if this journey into the unknown inspires you as much as it inspires me, if you want to continue exploring the mysteries that make our universe so fascinatingly impossible, subscribe to the channel and turn on notifications. Because each video is a new piece of the cosmic puzzle we're assembling together. After all, knowledge about our place in the cosmos is just the beginning.